Okay, a bit of organic chemistry. So we've got butane there. We have to say, what is the empirical formula of butane? Okay, now empirical formula, that's the lowest ratios one, right? So just write out what you've got, which is C4H8, 9, 10, okay, H10, but we want the empirical formula, so lowest ratios. Can we divide 4 and 10 by a common factor? Yes, we can. It's 2, and that gets C2H5. We can't go any lower than that. So therefore, the lowest ratios, 2 and 5, C2H5 is the empirical formula, okay, of butane. Right, complete this table. Right. Ethene, there's the structure. Yep, that's correct. Propene, pro means 3 carbons, so C3H6. Propene, so it must have an ene in it, like that. So let's start with that, let's draw that. So I said, what did I say? 3 carbons, propene, with a double bond. So 2 of them have a double bond between them like that. And there's the 3rd carbon. Okay, so that's the backbone, if you like. And now we just fill in the hydrogens, and if we've done it correctly, there should be 6. So this carbon, there's space for 3 more bonds, because carbon forms 4 bonds. H, H, H. That carbon already has 3 bonds, so there's room for 1 more hydrogen. This one already has 2 bonds, so there's room for 2 more hydrogens. Quick check, should be 6 hydrogens, 1, 2, 3, 4, 5, 6. Yep, and that's the structure of propene. Right, the molecular formula of ethene. Well, eth is 2, and it's an ene, so I was going to draw it, the structure, but no, he wants the actual formula. Right, well, what's the formula of this? It's molecular, so we have to give the total number. So it's C2 and H4. C2H4. That's the molecular formula. The empirical formula would be CH2, because that's the lowest ratios. So just going back to butene, that's the empirical formula. Okay, and that's the molecular formula. That one there. Okay? Right. The mark scheme for this, if you've got it, is wrong. They put C5H10 there for some reason. C5, that's pentene. So that's correct. Ethene is C2H4. Right. Okay, now we're reacting butene with steam. Butene, steam. Steam is just water in gaseous form. So it's water, okay? Butene, steam, to make butanol. Right, calculate the maximum mass of butanol that can be produced when 1.4 kilograms of butene reacts with excess steam. Okay, they've given us the relative atomic masses here. That's very nice of them. They've even given us the relative formula mass of butene. Okay, making life pretty easy for us. Okay, right, now with these sort of questions, write out the reaction that you've got. Okay, that's first thing. Next thing, make sure it's balanced. It is balanced. And then in columns underneath every molecule, write everything that you know about it. Okay? What do I mean by this? Well, we can work out the relative molecular masses of each of these molecules from this, okay? So write that down. That's something you know, so write it down. So we've been told that it's 56 for butene. Now, also include the unit. If the relative atomic mass of butene is 56, then that means butene weighs 56 grams per mole. Okay, always include the unit and write it exactly like that. Don't write it like this, grams per mole at an angle. Write it like that. Okay? Right. Water. 1 oxygen, 2 hydrogens. 16 plus 1 plus 1 is 18 grams per mole. We won't actually use that, but no harm in writing it in. Okay, butanol. C4, that's 12 times 4 because carbon is 12. 9 plus 1, it's got 10 hydrogens and it's got 1 oxygen, which is 16. So that is 48 plus 10 plus 16, which is 58, 68, 78, 74 grams per mole. Okay, so in the column underneath, write it in. Butanol is 74 grams per mole. Okay, so we've written down the relative molecular masses, but we know more, so we're not finished with this stage yet. We know that we have 1.4 kilograms of butane. So write that underneath, butane. We have 1.4 kilograms. Okay? Do we know anything else? No. That's it, okay? So we've written underneath all of the molecules, everything we know about them. What do we do next? Next, in one of the columns, there will always be 2 things, okay? And when you have 2, you can work out the third. And it's this column. There are 2 things. Now, what do we do? Look at the units. This is why you must write in the units, okay? We've got grams per mole and kilograms. First thing is to rewrite this in terms of grams. 1.4 kilograms is 1,400 grams. Now look at the unit. We've got grams per mole and grams. What do? We have to divide that by that. We're going to do 1,400 grams divided by 56 grams per mole. How did I know that we had to divide? By looking at the units, which is why you must write in the units. If you divide something that has in units of grams by something in units of grams per mole, the grams cancel, and when you divide and divide again, the moles flips up to the top, so it ends up on top, and that becomes 1,400 divided by 56 moles. So when we stick that in the calculator, we've got something in units of moles. So we've worked out the number of moles of this. So that's why you must always write in the unit, and looking at the units tells you what to do. That's how I knew how to divide in this case. So 1,400 divided by 56 is 25 moles. Okay, once you've worked it out, write it in the column. We know that we have 25 moles of butane. Okay, where do we go from here? We're looking to work out the mass of butanol. Okay, and at this stage, you look at the big numbers in front of the molecules. That tells you the molar ratios. Now the big number in all 3 cases is 1. There's an invisible 1 there, okay? Sometimes it could be a 2, a 3, or a 5, or a 6, whatever. But in this case, there's one of them plus one of them makes one of these. Okay, so there's that invisible 1 there, which means there's a 1 to 1 molar ratio of butane to butanol. We've worked out the number of moles of butane, so therefore 1 to 1 ratio, we can write in under butanol 25 moles without any calculation, because we know there's a 1 to 1 molar ratio, so 25 moles to 25 moles. Okay? So, what next? We now know two things about butanol, which means you don't even have to do any thinking, you just automatically work out the third. If you know two, you can work out the third, just like here. And again, write the units so you know what to do. We've got grams per mole and moles. So if we multiply them, the moles will cancel and we'll be left with something in units of grams, which is mass, which is what we want. So we do 74 grams per mole, right in the unit, times 25 moles. Okay, moles on the top, moles on the bottom, they cancel and we're left with grams. So that is 74 times 25 is 1,850. Okay, and we're left with grams. Bloody pen. And that is 1.85 kilograms. Okay, so we've done it. We have 1.85 kilograms of butanol. And that is how you should do these sort of questions. Good. I shall bin this blue pen. Okay. Right, what type of reaction takes place between butene and steam? So what type of reaction is this? Is it addition, dehydration, substitution, or neutralization? It's an addition reaction, okay? Because you've got two molecules and they become one molecule. You're adding them together. The water is adding onto the butane, okay? So it's addition, which is A. Okay, it's not dehydration because you're not removing water, you're actually adding water. It's not substitution, that's when one molecule comes in and kicks out another, that's not happening. And it's not neutralization, there's no acids and bases and alkalis involved. Okay? It's an addition reaction. Can I write that down somewhere? Why not? It's an addition reaction. Right, what three hydrocarbons are shaken with bromine water, which is orange. Haha, good choice. Comment on the structures of X, Y, and Z. Okay, so X, I'm going to use yellowy green for colourless. Okay, X remains colourless. Y remains colourless, and Z stays orange. Okay, so we have to comment on the structures of X, Y, and Z. No problem. Well, 2 marks. First thing, X and Y, because they're being shaken with bromine water and the bromine water goes from orange to colourless, that means that X and Y must have at least one double bond in their structure. So X and Y have at least one double bond. X and Y both. Okay, both an X and Y have at least one double bond. However, it doesn't mean they're the same molecule. Okay, you can't conclude that, so you might as well write that down. But they may or may not, may not be the same. Okay, the only conclusion you can say for sure is that they have that they both have at least one double bond in their structures, but that's the only thing you know about the structure. Okay, you don't know the complete structure. Right, you can also say that because the bromine water stays orange for Z, then Z contains 0 or no double bonds. Okay? So, quick bit of revision. Why is this the case? Well, that's the 2 marks in the bag. Okay. So why is this the case? Well, you just got to learn. It's a classic test in chemistry. It's a test for the presence of double bonds like that or like that. Okay. If you mix this compound or any compound containing double bonds, if you shake it in bromine water, the bromine reacts with the double bond. Okay, so bromine is diatomic, Br like that. Okay, and bromine water is just that in water. And if you add a compound with a double bond in it, this bromine reacts with the double bond, and this bromine-bromine bond is broken, and that bromine-bromine bond in water is what gives it the orange colour. So if there are double bonds present, carbon-carbon double bonds, they break that bond, and that's why it loses the orange colour. Okay? So it actually ends up that bromine on that carbon, that bond broken, that becomes a single bond, and that bromine on that carbon. Okay? So as you can see, the bromine-bromine bond is broken. But just remember that the bromine water test is a test for the presence of double bonds. If it goes colourless, then there's a double bond present. If it stays orange, there are no double bonds present. There we go.